All right, on to the next piece of notes. Today we're going to talk about a thing called inertia. And what inertia really is according to your notes, it says it's the tendency of an object, excuse me, to resist any change in its motion. Right? On this idea, the way in which I always like to describe this is I was thinking maybe we go outside and play some kickball. I don't know if I hope that you guys played kickball when you were like in elementary school, but I don't have one of those like rubber kickballs. So what we're going to do is we're going to play it with a bowling ball. All right. So if you can imagine trying to kick a bowling ball, it's probably not going to go really well, especially if one person like rolls the bowling ball up to another person and then that person tries to go up and try and kick the bowling ball while it's coming one direction. They got to try and exert a force on it to get it to go the other direction. I'm laying odds I probably better have an ambulance nearby for a bunch of broken legs or broken feet when they try and do this. Now, why is that? Right, you're probably saying to yourself, well, because it's really heavy. Well, don't use the word heavy in science. Use the word it's got lots of mass. All right, it's got lots of matter to it. So once we get that bowling ball moving, what does that bowling ball want to do? Well, it wants to keep going. It don't want to stop. Right. So you have to put a whole bunch of force into it to try and get it to go back the other way, or try and even get it to stop, let alone try and get it to go the other direction. Right. So you got to put gobs of force into it. That's what inertia is. Inertia is, it's that tendency of that object to just keep doing what it's doing. Right? So if the bowling ball is moving this way, it wants to keep moving that way. Right? Now what if I said, okay, well, let's make this easier. Let's not have somebody pitch the bowling ball for those people that are going to try and kick it. Let's just set it in one spot, kind of like T-ball, right? And then you just come up and kick it. Is it still going to be easy? Nah, it's probably not. It's still going to hurt. Because trying to get that bowling ball to all of a sudden accelerate and go in another direction out into the field so that you can actually make it to first base, it's still going to be hard. Why? Because again, it's got mass. It's got a whole bunch of mass. And you got to put a gob of force in there to try and get it to accelerate, right? To go out in the field. Oh, listen to that. There was that equation, force equals mass times acceleration. That was something that we talked about earlier, F equals M times A. So hold on one second. All right, so to try and get that ball to go the other direction, again, that's force equals mass times acceleration. So if I got a lot of mass and I want it to accelerate in another direction, it's going to take a whole bunch of force, right? So instead, when we play kickball, we want to use something that's lighter. So we use that rubber ball that doesn't have as much mass. Then it doesn't take as much force in order to make that little bit of mass accelerate and go in another direction. All right. So that's the concept behind inertia. Is that the way I like to look at it is objects like to do what they're doing. All right. If they're traveling in one direction, that's what they want to do. They just want to keep going in that direction. If they're sitting in one spot, then they want to stay in that one spot and not go anywhere, right? And it's going to take gobs of force in order to change either situation. If it's traveling in one direction, it's going to take a bunch of force in order to get it to change its motion, right? Whether it be get it to slow down, whether get it to turn, whether to get it to go back the other direction, right? Whatever that is, it's going to take a bunch of force to get it to do it. If the object is just sitting still, then it's going to take a bunch of force to get it to do something again, right? So the next thing in your notes, it says a moving object travels in a straight line, and an object at rest stays at rest unless a force is applied, and that's Newton's first law of motion, right? With Newton's first law of motion, again, the objects are going to do what they want to do, okay? Another example would be, think of, again, go back to the idea of bowling ball. Let's go bowling, right? When you take that bowling ball and roll it down the lane, when it hits the pins, what's the bowling ball want to do? Well, it wants to keep going, and that's what we want it to do, so it'll go through and knock down the pins. What we don't want to happen is that the bowling ball hits the first pin and stops, right? That's not what we want it to do. Those pins don't have enough force to exert back on the bowling ball to get it to stop, unless, and this is always something that I find, I know, kind of maybe weird, but when I go to a bowling alley, I love watching people that have a really lightweight ball and they roll it down the lane and it hits the first pin and all of a sudden it gets like bounced off to the side. And it's like, you know, if you use a ball that's got more mass, then it wants to keep going through. Right? So that's something else you can look at. I love making things that you can watch it out in the real world. Watch that next time you go to a bowling alley and watch based on the mass of the bowling ball as to what it does when it hits the pins. All right, so letter C in your notes says inertia depends on two different things. Number one, mass. Well, we talked about that a whole bunch already. The more mass, the more inertia. So the harder it's going to be to get it to start moving, or the harder it's going to be to get it to stop moving, either way. The other thing is, and a way which I like to describe this is, well, let's use something that's really, really small, right? And I want to play catch with a bullet. Well, that ain't going to work, because if somebody like shoots a bullet at me, I'm not going to be able to stop it. But man, that bullet's really, really, really small. It don't have very much mass. Well, then why can't I stop it? Well, the problem is it's going so fast. And because it's going so fast, it's got a lot of inertia, and I got to exert a whole bunch of inertia into that little bitty mass in order to get it to stop. All right. So the other factor in regards to inertia is velocity. Greater velocity equals more inertia. The faster something goes, the harder it is to get it to stop. Okay. Now, another thing that I love to talk about in this, and this will come back in another chapter later too, is think about a car. Right? And if it's wintertime, which by the time we do this video, we will have already gone through the winter, because this is going to be in the spring, that when you come up on a corner in your car, you want your car to go around the corner. If it's really slippery out, what do you have to do in order to make sure that you get around that corner? Well, number one is you got to slow down. Right? You got to lower that velocity, because what does your car want to do when it gets to that corner? Well, according to inertia, what it wants to do, keep going straight. So you may turn the steering wheel and the car just keeps going. Right? Why does it keep going? Because of inertia. It wants to travel in a straight line. Excuse me. So what we've got to do is we got to slow down enough to make it so that I can get another force to overcome that inertia, which that then takes us to the next set of notes, which happens to be friction. What I've got to do in that car going around that corner is I've got to slow down enough so that the friction between my tires and the road is enough or greater than the inertia, so that that friction will cause the car to go around the corner. If I go too fast and my inertia is greater than the friction, then my car is going to keep going straight and I will skid out as I go around the corner. Right? So friction actually is a force. Right? I know that sounds crazy, but this, right, the friction that occurs between my hands, that is a force that's going on. Right? It's the force that opposes motion between two surfaces that are touching. That's why when I do this, I feel my hands get warm, right? Because that friction produces heat. If I do this, and I'm not getting any friction really, because they're not touching each other. Those surfaces got to touch each other in order to get friction. Okay? What does friction depend upon? Number one, kind of surface. Rough versus smooth. If you've ever seen a NASCAR tire, the tires on race cars, they don't look like the tires we have on our cars. Our cars have all sorts of little grooves in them. It's called tread. But a NASCAR tire, smooth. Right? But it's also it's a really, really soft type of rubber that it's really kind of like sticky, so it sticks to the road. So they keep it smooth so that it gives them lots and lots of friction so that they can go around corners a whole lot faster. It's a really, really soft metal, or soft rubber, so that it gives them more friction, so it sticks to the road so that they can go around the corners even faster. Well, now you look at that and go, why don't we use those on our cars? Because then we could go around corners a whole lot faster. But have you ever noticed how often NASCAR racers change their tires? They may race a 200-mile race or even a 500-mile race. And in a 500-mile race, they're going to change their tires 3, maybe 4 times. So imagine, go home and ask your parents, how long does it take you to put 500 miles on your car? How will the odds? They would probably tell you it's only going to take a couple days. Maybe if they don't have a long drive to work, it might take them a week to do 500 miles. So imagine then within a week, if you had to change your tires 3, maybe 4 times. Oh my word, that would be expensive, all right? Because tires are about $100 a piece, so that's $400 every time you got to change all 4 tires in your car. So do that, let's just say 3 times in 1 week. That's like 3 times 400. That's $1,200 a week in new tires if we use NASCAR tires on our cars. So we don't use those because it would eat them up way too fast. So what we do is we use a harder rubber that reduces the friction. We don't get quite as much friction, but we still get enough to get us going down the road. And what we have to do is we just got to go a little slower going around the corners. The other aspect that influences excuse me, friction is the force that presses those two surfaces together. Okay? The more that force is pushing down on it, then the greater the friction. The less it pushes down, the less the friction. Right? And one of the things that Ford Motor Company has done within about the last 5 to 7 years is they, in their F-150, they've switched it to a lot of aluminum. Now, why aluminum instead of iron? Well, aluminum has a lot lower mass. Because it's got a lot lower mass, and that means their vehicles weigh less. If they weigh less, then they get less force pushing down, and therefore they have less friction. And friction is the thing that takes away fuel mileage on a car. So if we can reduce that friction level, then we can get better gas mileage on a car, right? Or gas mileage on the truck in this case. So you'll see that cars are getting more and more aluminum. Now, the one unfortunate piece also, aluminum is more expensive than iron. So that's a factor that comes into play for Ford Motor Company if they want to use aluminum to make their trucks, is it costs more to make the truck. But then they try and sell more of them because people look at it and go, well, I can get better gas mileage. So if they can sell more of them, then they can bring that price down a little bit. But it's and it's all has to do with the friction and trying to get better gas mileage. So I think that's it. Yep. That's all my notes. So remember, inertia, that's the tendency an object wants to do what it's doing. Wants to keep going if it's going, or wants to stay sitting still if it's sitting still. Right? And then the force that causes objects to change is friction. So, and I'll jump back for a second and go, if you roll a ball, we just said that that ball wants to keep doing what it's doing. So you roll a bowling ball across the floor. Is it going to go and 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 go forever? No, we all know it's going to stop at some point. What makes it stop if it doesn't run into something? Well, it's friction of that bowling ball with the surface that it's on. And remember, that's a force that opposes, goes against motion. So that friction with the floor actually causes the bowling ball to start slowing down and finally stop. And then that friction turns into heat. I know you go, I don't pick up a bowling ball and feel like it's hot, but there is a little bit of heat in there, and that little bit of heat goes floating off into the atmosphere, which is what causes that bowling ball to stop its motion. So that's inertia and friction. All right, that concludes our notes for today. You have a good day. We'll see you.